Welcome to this explainer. Today, we're pulling back the curtain on how machine learning algorithms actually categorize the world's information. Like how your email just magically knows what's spam, or a bank instantly decides whether to approve a loan. Well, it all comes down to classification models. We're going to focus in on the mathematical magic behind how these systems learn to make binary decisions.
Here's the pipeline we're following today. Data splitting and stratification, logistic regression and the S-curve, support vector machines, the confusion matrix, and finally, precision, recall, and ROC. Let's get right to it.
Section 1, Data Splitting and Stratification. Preparing the foundation. Because before any algorithm can learn a single thing, we have to prep the data.
Think of training a model kind of like a student prepping for a test. You give them a textbook to learn from, that's your training data, but you test them on completely unseen questions to see if the concepts actually clicked. Now, if you just randomly chop a dataset in half blindly, you might end up with a totally imbalanced split. Imagine all your yes answers end up in the training set and all the no answers fall into the test set. The model learns absolutely nothing useful. Stratification fixes this. It ensures that the proportion of different categories remains consistent across both sets, giving us a beautiful, perfectly balanced 50% split for the machine to actually learn from.
Section 2, Logistic Regression, the S-curve. Mapping probabilities. So with our data properly prepped and balanced, let's jump into our first major classification tool. Logistic regression is our absolute go-to for binary-dependent variables. We're talking about situations that can only be one of two states, pass or fail. True or false, yes or no. But wait, why not just draw a standard straight linear regression line to figure this out? Well, it completely fails to classify discrete yes or no points. A straight line eventually shoots off into infinity in both directions, but probability has strict rules. It has to be positive, and it has to be less than or equal to 1. A straight line might predict a value of -2, or +5, which makes literally zero sense when you're just looking for a simple percentage chance of something happening.
So here's the fix. We just swap out that straight line for an S-shaped logistic or sigmoid function. This thing works like magic. It maps those predicted values into pure probabilities, strictly between 0 and 1. Notice how the curve just flattens out at the top near 1.0 and at the bottom near 0? Beautiful. Then we simply set a threshold, say 50%. If the S-curve puts a data point above 0.5, boom, the model predicts a yes. If it falls below, it predicts a no. It is just an incredibly elegant mathematical solution to bounding our predictions.
Section 3, Support Vector Machines, Finding the Optimal Boundary. While logistic regression is all about calculating probabilities, SVMs take a totally different geometric approach. To really demystify SVMs, we first need to define a massive buzzword, the hyperplane. I know, it sounds super sci-fi, right? But a hyperplane is simply the geometric boundaries separating our data classes, depending on how many dimensions we're working in. In one dimension, it's a point. In 2 dimensions on an x and y axis, the boundary is a simple flat line. If you step up to 3D space, it becomes a flat plane, like a sheet of paper. And anything 4 dimensions or higher, that's what mathematicians call a hyperplane. Now, the entire goal of an SVM is to draw this hyperplane in a way that maximizes the margin. The margin is the actual physical distance between the nearest data points of the competing classes and the dividing line itself. We call those nearest points or support vectors. Imagine you're building a road between 2 different neighborhoods. You want that road to be as wide as possible without plowing into any houses on either side, right? That wide road is your maximum margin. It makes your model way more robust and far less likely to make a mistake when fresh, unseen data rolls in. But what if your data is a total mess, like a bullseye pattern where it's literally impossible to separate the classes with a flat line on a 2D graph? This is where SVMs really flex their muscles, using something called the kernel trick. It's this genius mathematical shortcut that implicitly projects that jumbled 2D data up into a 3D space. Suddenly, data points that were tangled all together on a flat surface pop up and separate in 3 dimensions, allowing a perfectly flat 3D plane to slice right between the classes. It is a true game changer for handling highly complex, nonlinear real-world data. Section 4, the confusion matrix explained, grading the model's accuracy. Okay, so our models are making predictions, but how do we actually grade their success? Basic overall accuracy can be a terrible evaluator for class imbalance data. Think about it. If 99% of transactions are totally legit and only 1% are fraud, a completely useless model could just scream legit every single time, boast 99% accuracy, and entirely miss the fraud it was built to detect. Enter the confusion matrix, Ironically, it's actually designed to clear things up. It's an error matrix that breaks down exactly where the algorithm guessed right into true positives and true negatives, and crucially, where it guessed wrong, false positives and false negatives. Laying it out like this lets us see exactly how our model is failing, not just that it's failing.
Section 5. Precision, Recall, and ROC. Moving beyond basic accuracy. Because from that matrix, we can extract much more powerful metrics. You really have to choose what matters most for your specific problem. Take precision. You'd prioritize high precision if false negatives aren't a huge deal, like a spam filter. A few spam emails getting into your inbox is fine, but it is totally unacceptable if a vital work email gets thrown into the spam folder. On the flip side, you want high recall, also known as sensitivity, for something like a medical diagnosis. In medicine, missing a disease, a false negative, has a devastating, potentially fatal cost. And hey, if you just need a single number that finds a balance between the two, you calculate the F1 score. Finally, we visualize the model's overall threshold performance using the AUC ROC curve. ROC stands for Receiver Operating Characteristics. This graph plots the true positive rate against the false positive rate. That dotted diagonal line right through the middle, that represents a purely random guess, literally like flipping a coin. The solid lines arching toward the top left represent our actual models. We measure the total area under that curve, the AUC. So basically, a greater area under the curve means the machine is doing a significantly better job at confidently distinguishing between the positive and negative classes. Obviously, we always want our model's curve pushed as far to the top left corner as geometrically possible. High true positives, absolutely zero false positives. But looking at that dot labeled perfect classifier leaves us with a pretty provocative final thought. Honestly, given the incredible complexities, the noise, and the total unpredictability of real-world human data, will we ever actually achieve that elusive perfect classifier? Or is machine learning destined to just always be an incredibly sophisticated game of balancing errors? Think on that. Thanks for joining me on this explainer. Keep asking questions, and I'll catch you in the next one.